All right, so 3.4 was a reprieve from truth tables, right? No truth tables in 3.4. No truth tables in 3.5 either. All right? Have no fear, they're coming back in 3.6. We will deal with them one more time before the end of this chapter. But we're going to take a look at a different kind of diagram. This E-U-L-E-R is not pronounced Euler. It is pronounced Euler. Okay? I promise it's pronounced Euler. Had an argument with a student last semester. We even looked it up on the internet so I could show him. It's Euler. It's because it's not English, right? This is not an English mathematician's name. All right, so this is Euler.
A common pronunciation.
All right, so what we're going to be working with in both 3.5 and in 3.6 is determining if arguments are valid. So give yourself sort of the description or the thinking that if you were a lawyer and you wanted to convince somebody that something was true, you have to be able to form an argument that works, right? The argument has to follow. And that's what we're going to be working with in this section and in section 3.6, which is the last one in chapter 3. So there are two different things we're going to be talking about. Valid arguments state that when all the premises are true, it forces the conclusion to be true. In other words, if I buy into certain facts at the beginning, the rest of it has to follow. If I can show you that the first pieces actually work, then you have to then follow through with my argument and say, then yes, I have to come to the same conclusion you do. Okay? And then an invalid argument is not valid, exactly the opposite, right? And it's also called a fallacy. We'll use those phrases interchangeably. And what we're going to see in this class, or in this section, is Euler diagrams. Euler diagrams look very much like Venn diagrams, and there are three types. So I'm going to show you these three types, and then we'll stop for today. One type of Euler diagram has a circle inside of another circle. One type of Euler diagram has two circles that overlap. And then a third type of Euler diagram has two circles that are disconnected entirely. I'm going to give you an example of each one so that you can get a feel for how this works. Example on the first one, all dogs are animals. So the inside circle would be dogs, and the outside circle would be animals. Clearly, there are other things within the animal circle. Some potentially overlapping with dogs, depending on how you describe dogs. Some potentially not, but other things are there, but all of the dogs, the smaller circle, is inside the bigger circle for animals. Look good? All right. Second one would be something like this. Some students attend OBU. How about, let's say, not students, let's say some freshmen. That would be better. So one of these circles, and it doesn't matter which one, is a circle for freshmen. And clearly it has freshmen here. It has freshmen at OU. It has freshmen at Xavier. All these different freshmen, okay? The other circle is people attending OBU. Clearly some of them are freshmen, some of you. Some of you are not freshmen and you're also attending OBU. So there is an overlap between these descriptions, but there's not one contained entirely inside of the other one. Are you with me? All right, last example. No, we'll do birds today. No birds live at my house. And I'm out of space. I'm writing on top of my diagram. You don't need to do that. But this picture right here is birds. I don't do birds. And this picture right here is things at my house. We have cats. We have dog. We do not have any birds. Okay? Completely disconnected circle. There is no overlap. And we'll stop for today.